Okay, so this morning there was a goof up with the live stream. As a result, the live stream didn't quite go through. So this is going to be a quick re-recording of the lecture where I'm just going to go through the notes. This is going to be much faster than how we did it in the lecture. So I'll recommend that people watch it at a lower speed or pause often if needed. Okay, so last time we were looking at this notion of vertex expanders. Uh, and this, in some sense, is perhaps closer to the notion of what we often think of as expansion, which is that when you have a small subset of vertices, by small, I just mean that its size is bounded by some parameter k. I would like to say that the neighborhood size is at least a factor a larger than the original size. Okay, in some sense, that all sets of up to k size sort of expand with their notion that the neighborhood is a little larger. Uh, and this is often not amenable to analysis as nicely as we would like. So in some sense, the different notion of is what is called spectral expansion, and this is what we'll be working with most of the lecture. In fact, most of this part of the course, and that is given by from the notion of random box mixing well. So the this definition here sort of indicates the following: you fix any probability distribution that you care about. And you would like to say that after you do a few steps of the random walk, you somehow get closer to the uniform distribution, which I'm referring to as U. Uh, and this basically sort of says that the distance of the probability distribution from the uniform, uh, and you want to compare that with what the distance is after you take one step of your random walk. Okay. And we would like to somehow say that the distance to uniform is somehow a little smaller than the original distance to uniform, in the sense that these vectors get shrunk. And this is just an alternate way of looking at the same thing, because any vector p minus u is going to be orthogonal to the uniform distribution. And this then looks like you look at all vectors that are orthogonal to the uniform distribution and you ask how much does m shrink such vectors. Okay, and this is defined as lambda of G, where M refers to the random walk matrix associated with G. And the spectral gap, which is often called gamma of G, is just the difference between how far away lambda is from 1. And this is always going to be a non-negative quantity. And this is going to give us often a measure of how good an expander it is. The better the gamma, the better the expander is. Or rather, the larger the gamma, better the expander is. Okay. And ideally, what we would like is to come up with some family of constant degree graphs, let's say degree 100 or something, with some promise that the spectral gap is at least some fixed constant we have in mind, let's say 0.01 or some such thing. Okay. And we would like to build such graphs where the number of vertices is growing, like it's a family of graphs, but these are all graphs that are going to be sparse in the sense that the degree is quite small, but nevertheless, they have good expansion properties. Okay. And something that we mentioned last time was this really cool fact, which is called the Expander Mixing Lemma. And it more or less captures what you want from an expander. So what this says is, suppose you have a gamma spectral expander, and let's say we are dealing with d-regular graphs. We will soon generalize this to arbitrary, not necessarily regular graphs. Then, if you have two sets of vertices, S and T, some subsets of vertices that you have, and let's say the volume of S is like alpha, by which I mean it's like alpha and alpha fraction of vertices are in S, and T is some set of size beta n. Then is you sort of it gives you a way of getting a sense of how many edges do I have between S and T, normalized by a certain quantity. Maybe a better way to think of what is happening on the left-hand side is that this expression, alpha beta, can be thought of as saying, if you just pick two vertices x and y at random and ask what is the chance that x is in S and y is in T, and if x and y are chosen independently with no connection between them, then this will be alpha beta just by definition of the densities of S and T. On the other hand, the left-hand side starts looking like you pick an edge at random in this graph, and you ask what is the probability that the first, like one endpoint is in S and the other endpoint is in T. Okay, and that's what the left-hand side looks like. And the expander mixing lemma is sort of saying that if you pick an edge at random and then you're trying to argue something about what happens to the left vertex and the right vertex in some sense, this more or less behaves like as if you pick those two vertices uniformly at random, in the sense that the difference between this number and this number is small if you believe that lambda is small. Okay, and something that we mentioned last time but we didn't prove was the fact that when you have a spectral expander, you also have a vertex expander with appropriately set parameters. And the first thing we are going to do is look at the proof of this fact. Okay, so formally speaking, the statement is the following, that you have a deregular digraph that happens to be a gamma spectral expander. Then I want to say that you fix a constant alpha that you care about that sort of measures what up to what size do you want things to expand. And it says that you do have an expansion parameter that is some expression involving lambda and alpha. So just to point out, notice that the denominator looks like some convex combination of lambda squared and 1. And therefore, it's going to be some number between lambda squared and 1, which means it's going to be bounded away from 1. And the denominator is something that is smaller than 1, so therefore, this reciprocal is going to be something larger than 1. So in some sense, it is an expansion that you witness. Okay. And all of these proofs sort of follow a very generic template, which is to set up an appropriate vector that tries to capture the problem, the combinatorial interest that you have in the problem, and then just let linear algebra work its way through. Okay. So what we are going to do now is we want to basically show that for every set S, which has size, maybe for now, I'm just going to say the size is exactly equal to alpha times n. I want to say gamma of S is large. Ideally speaking, we should do this for all sets of size utmost alpha n size, but for the sake of just doing it quickly, I'm going to do this. So the way we are going to do this is by just starting with the uniform distribution on the set S. Let P be that vector, which is the uniform distribution on the set S. And the first thing is I want to write P as U plus P minus U. And if you notice, look, the sum of the entries of P is equal to 1 because it's a probability distribution. And that's the same for the sum of the entries of U, which means that it better be the case that the sum of the entries of P minus U is equal to 0. And that's another way of just saying that P minus U is orthogonal to U. So in some sense, what we have just done in this expression is that we have written P in the component along the uniform direction and the component which is orthogonal to the uniform direction. It just so happens that the component along the uniform direction is exactly U. Okay. So now that we have that, Pythagoras theorem will tell us that the norm of P squared is the norm of U squared plus the norm of P minus U squared. And the norm of P squared is nothing but 1 over S. And the norm of U squared is 1 over N. So together we have this equation, which is that P minus U, the norm of P minus U squared is 1 over S minus 1 over N. Okay, this is just something that we have at the moment. But now let's look at what happens after we take one step of the random walk. And let's call that vector as Q. And the reason we are going to look at one step random walk is because the support of Q is basically the neighborhood of the set S. And that's what we want to get a handle on. So it makes sense to sort of say, let's take one step from the uniform distribution on S, and maybe from the norm of Q, etc., we'll have a sense of how large the neighborhood is going to be. Okay. So we'll do exactly the same thing like we did for P. And this, again, by Pythagoras theorem, will tell you this. And this is the point where we can use the expansion, which is that because Q minus U is a vector that is orthogonal to the uniform distribution, expansion tells us that Q minus U was nothing but P minus U, the whole transpose times M. So this was so Q minus U transpose, this was nothing but P minus U transpose M. And we know by expansion that M shrinks these vectors by a factor of at least lambda. And since we are dealing with square norms, this immediately tells us that the norm of Q squared is at most the norm of U squared plus lambda squared times P minus U squared. And this is coming from the fact that the graph that we are dealing with is a spectral expander. Okay. Now plugging in what we have above this, we get some equation. That is to say that the norm of Q squared is at most this quantity. But at the moment, we still haven't been able to relate the norm, the support of Q to this. And let's do that in the most obvious sense, which is to just use some Cauchy-Schwarz so that you bring in the support. So I just focus on the summation of the sum of all the entries of Qi, of Q, which is going to be equal to 1 because it's a probability distribution. And a simple Cauchy-Schwarz will tell us that this is at most the norm of Q times the norm of the one vector that is supported on the support of Q. And therefore, that is going to be at most square root support of Q. And like we said before, the support of Q is exactly equal to the size of the neighborhood. So this implies that 1 over the size of the neighborhood is at most, this is at most the norm of Q squared by just rearranging the above equation and plugging in what we had from the previous thing, you get some relation between the neighborhood size and the size. And with some rearrangement and using the fact that the size of S is never more than alpha times N, you get the vertex expansion claim of the lemma. I mean, it's not a hard proof, but it's one just needs to go over it carefully. Okay, so now we're going to start switching to just dealing with graphs in general, not necessarily a regular graph, because this is often convenient when you're dealing with situations where you maybe have a more general Markov chain and you want to study them. But we're not going to be looking at it in absolute generality. I'm going to focus on just undirected graph, but possibly not regular. Okay. And if you really want to know what's the most general setup that we need to have, we need to add a notion of what is called reversibility, which I'm going to not try and think too much about. But if people are really interested, this is what you should be looking at. Okay, so now let's say G is some arbitrary undirected graph. I'm going to define this matrix D. This is the diagonal matrix of degrees. So it's the ith diagonal element is just the degree of the ith vertex. Okay. And with this definition, let's define a random walk matrix, which is just D inverse times A, where A is adjacency matrix. Or in other words, the rows of the adjacency matrix are scaled so that they sum up to 1. And this is called the random walk matrix, and it's set up in such a way that it is row stochastic. So the rows sum up to 1. All right. Like in pictures, what does every entry of M really indicate? It basically says that if you start off with a vertex U and a vertex V, the UVth entry is just the probability that if I started at U, what is the probability that I end up at V in one step? Okay, and this is just the standard random walk matrix where every vertex, the random walk is just going to choose a uniformly random neighbor. And that's what this matrix captures. Now, whenever we have a matrix, there is usually 3 perspectives that you could take. And there are 3 different angles from which you can study this matrix. The first is where you want to think of the matrix acting on the right. I mean, think of it as an operator where the matrix shows up on the right, or think of it as an operator where the matrix shows up on the left, or think of it as a quadratic form. Okay. And when I mean think of it as a matrix when the matrix shows up on the right, what I mean is it's a transformation on row vectors. You have a row vector, P transpose, and you want to know what happens under the action of the matrix M. So that is the matrix acts on the right. Okay. And on the other hand, you could think of also it acting on column vectors, where now the operator shows up on the left. And the third thing is you think of it as a bilinear form where you're given 2 vectors f and g, and you have some notion of inner product that you care about. And you just study what does the inner product of f and mg look like. Okay, and that's the quadratic form associated with this matrix. Okay, and it will turn out that the random walk matrix that we are dealing with, all of these 3 perspectives are actually quite illuminating. Okay, so let's just focus on the first part now, which is that the matrix acting on the right. So let's say you have a row vector P and Q is what you get after you act. You sort of, you hit P with N. Okay. And if you were to write down coordinate by coordinate, this is what it's going to be. What is the vth coordinate of Q? Well, it's the appropriate sum that you have on the right hand side. Okay. And if you were to actually sum up all the coordinates of Q, and if you just write down what the expression looks like, because the matrix is row stochastic, we know that these sums are equal to 1. So you now basically get that the sum of the entries of Q is actually equal to the sum of the entries of P. Okay. And so another way to think of this is like, it tells you how the probability vectors transition. Like if you make one step in your random walk, and if your original distribution was P, your new distribution is going to be Q. And the fact that the sums are maintained sort of says that probability vectors stay as probability vectors. Okay. Or you could also intuitively think of this as if you imagine PU as referring to the probability that you are at vertex U, then PU times MUV is like sort of saying that if you were at once you are at vertex U, what is the chance that you now end up at V? Right? And summing up over all possible U is just asking what is the chance that you are at V after you take one step of the random walk. Okay, so it makes sense. Then, if you want to think about the evolution of the probability distribution, then you should be putting the matrix M on the right. Okay, so whenever you're dealing with probability vectors, it's often going to be good to think of them as row vectors, so that you know which side the matrix is going to show. Okay, now what about the action on the left? So in this case, it's often convenient to think of these vectors as some sort of potentials that you assigned to all the vertices in the graph. So let's think of it as a function. Rather than think of it as a column vector, you can think of it as a function that for every vertex assigns a number. And let's ask ourselves, what does MF look like? Now notice that MF at U is going to be this expression on the right-hand side. Now, which is different from what we had above. But here, the MUVs, the various, as you range over Vs, we know that MUVs add up to 1. And this, therefore, looks like, this is like some convex combination of the FVs that you have. So in some sense, what is happening here is like, the vector F is sort of getting averaged out over the neighbors at every vertex. In some sense, it's like F is like some charge that we added to all the vertices, and MF is the charge after sort of it dissipates, in the sense that every vertex decides to take its new charge to be the average of the charges it sees, or something like that. So, okay, good. So these are two slightly different notions, but they're both very useful in depending on the context that you're in. Okay, so the first question we can ask is, what is a function f that satisfies MF equals f? In some sense, what is the right eigenvector for the matrix M? Okay, and since it's an averaging operation, a vector that will not change under averages is like, a vector that's already a constant. If something is a constant, then no matter what average we're going to take, we're going to end up with a constant. And in fact, the canonical constant vector is just the all ones vector. So we'll write this as M of all ones equals all ones. All right. What about the probability distribution pi that somehow seems to satisfy? Oops, this is not what I wanted to say. This is pi transpose. So when is pi transpose M equal to pi transpose? Like for what value of pi? This is a little non-trivial. And one might think that this is going to be the uniform distribution, but it's not. But it's not hard to see that it can't be the uniform distribution in a general setting. Because if your graph had some very high degree vertices, and if you let a random walk evolve, you are going to be at the high degree vertex some more frequently than other vertices. Okay, so somehow it seems intuitive that maybe the higher the degree, there must be more mass that is added to that vertex on pi. And in fact, turns out that basically the probability distribution that satisfies this, in fact, has this property that it is proportional to the degree. If you set up a vector that is proportional to the degree, a probability distribution that's proportional to the degree of every vertex, it will turn out that pi transpose m equals pi transpose. Okay, so this is going to be one such vector. We will soon see a small calculation to see why that is the case. But there is a convenient way of thinking about what this vector pi is, which is you are picking up an edge uniformly at random from your graph and just say output the first vertex. So this distribution, or rather, we are now giving a random process to spit out vertices. This random process, the distribution that it assigns on the vertices is actually equal to the expression that we have on the left. Okay, so let's just see why this is the case. So I want to look at what the uth entry of pi transpose m looks like. Okay, so I want to look at the uth entry of pi transpose m, and this by definition is just equal to this. Okay, and if you write this down, what pi v is supposed to be based on this definition and what mvu is, etc., you'll notice that it basically just boils down to degree of the vertex u divided by twice the number of edges, which is the sum of all the degrees. Okay, so this should let you verify that the pi does satisfy pi transpose m equals pi transpose. And such a distribution is called a stationary distribution in the sense that it doesn't change from the random walk does not change this distribution. Okay. Now, given a particular stationary distribution, there's going to be a very convenient inner product to work with whenever we are dealing with these random walks of some undirected graphs, which is this distribution that's basically the usual inner product, but sort of weighted slightly differently. In other words, so the definition is going to be, we'll say that the inner product of f and g with respect to this stationary distribution pi that we just defined above is just going to be the following. You draw a vector, draw a vertex x at random according to the distribution pi, and just look at the expected value of f of x, g of x. Okay. So that's what the inner product is. It's easy to verify that this is indeed a bilinear form in the sense that inner product of f1 plus f2 with g is inner product of f1g plus inner product of f2g, and all the standard properties that you would want of an inner product. Okay, so this, if we were to expand it out, it really looks like summation fx gx pi x. The extra parameter that's sort of showing up here is pi x. That's the only difference it has from the standard inner product. Okay, and sometimes this is sort of succinctly also written as f transpose capital pi g, where capital pi refers to the diagonal matrix that's made up of the entries of pi. All right. Now that we have this inner product, we can go back to the third perspective of matrices that we had, which is to look at the bilinear form corresponding to the matrix, which is you want to study what does the inner product of f and mg look like. Okay, which by definition from the above is going to be this expression. Okay, if one were to sort of manipulate this a little bit, basically just expand out what does mg at x look like and rearrange terms so that you write down exactly what this inner product is, plug in all the values that you know so far, you notice something rather unusual. You notice that this entire expression looks like fx gx, the degree of x sort of cancels off. And what you have is a very, very intuitive definition that, or a very useful notion that you might want. You pick an edge of your graph uniformly at random, look at f at the left endpoint times g at the right endpoint, and take that expectation. That is what is captured by this bilinear form given by this matrix, which, as you can imagine, is a very, very useful notion because many times this is exactly what you want to somehow get your hands on. All right. And this, notice that because this on the face of it looked somehow asymmetric with respect to f and g, but this expression, because your graph is undirected, is actually symmetric with respect to f and g. So in fact, you somehow miraculously have that even though we defined a certain inner product, it somehow seems to be engineered in such a way that the inner product of f and mg is the same thing as the inner product of mf and g. Okay. And this property, where you want to say you can move the matrix on either of the two coordinates, is referred to, this property is called, M is said to be self-adjoint with respect to this inner product. Okay. And if you think about the fact that inner products are like you stick in the diagonal matrix pi, if you work that out, what you end up getting is that like pi m actually equals m transpose pi. And because pi is actually a diagonal matrix, this is like saying pi m is a symmetric matrix. Okay. So the inner product is arranged in such a way that we have this self-adjoint property that we want. Now, why do we care about these self-adjoint properties? The reason we care about the self-adjoint property is this beautiful theorem, which is called the spectral theorem, which we won't be proving, but I'll just state it here. And it's typically stated for symmetric matrices, where the inner product is a standard inner product. And symmetric matrix is indeed self-adjoint with respect to the standard inner product. But here is a more general statement for self-adjoint matrices. So a matrix is if suppose a matrix is self-adjoint with respect to some inner product, then turns out that there are real eigenvectors and eigenvalues that this matrix has. So that by itself would be surprising. In that even though you have a real matrix, it could be possible that some of the eigenvalues, etc., are complex numbers. But this tells us that the moment you know that your matrix is self-adjoint with respect to this inner product, you actually have like a set of real eigenvectors. Not just that, these eigenvectors are actually orthogonal with respect to the inner product defined here. Like whatever is the inner product that M is self-adjoint to, the vectors that you have are actually orthogonal, pairwise orthogonal with respect to that inner product. And you can always make sure that they are also orthonormal. Sorry, this should have been, if I is equal to j, then they are equal. Otherwise, then the dot product is equal to 1. Otherwise, the dot product is equal. Okay, good. So that's what the spectral theorem says. And in other words, what this seems to suggest is that your ambient space actually has a basis of orthonormal eigenvectors, which is super convenient. All right. So now notice that if M is actually row stochastic, which is, like we arranged for it in such a way, then MF is, as we mentioned earlier, is an averaging operation. So every vertex is going to average out the values that you see among the neighbors, which in particular is going to mean that the largest value of MF is never more than the largest value of F. Okay. So that immediately tells us that the eigenvalues for these row stochastic matrices that we have is actually going to be at most 1 in absolute value. And because we already know that, the all ones vector is an eigenvector with eigenvalue 1, in some sense, we already know what lambda 1 is. This is equal to 1. And this is the all ones vector when it comes to row stochastic matrices. Okay. And so pictorially, you can think of the real line where there's -1 here and +1 here. And we know that at +1, lambda 1 sits, which is lambda 1 is equal to +1. And we know that all eigenvalues are in this interval. They don't exceed 1. They don't go beyond 1 or -1. They're somewhere within here. We don't quite know where they lie on this line. Okay. And we are now moving towards a notion of redefining the notion of spectral expansion. So if you recall, the spectral expansion was defined based on these two norms. So it'll be good to have a sense of what two norms should we be looking at. And the natural way of defining the two norm is with respect to the inner product that seems to be most relevant here. So you just say that the two norm squared of a certain vector is just the inner product of f with itself, where the inner product is the inner product that we have been using. All right. So now so suppose f is some arbitrary vector. Because we know that the eigenvectors v1 through vn form a basis, we can write f as some linear combination of alpha of v1 through vn. And let's say the coefficients are actually alpha 1 through alpha n. Okay. A super convenient notion now is that if we now care about the two norm of the vector f, it's just going to be summation alpha I squared because of Pythagoras theorem again. Because the vi's and vj's, I mean, different vi and vj, they're actually orthogonal to each other. And since the norm of each vi was set to 1, I mean, this is going to give us a decomposition of, just say that the norm is just the sum of squares of the coefficients. Okay. And the matrix M also acts on this F in a very, very nice fashion, which is that because I know that each of the VIs are eigenvectors, all it does is scale each coordinate by the corresponding eigenvalue. Okay. And therefore, the two norm of MF is also very nice, which is just going to be summation lambda I squared alpha I squared. Because the new coefficients are lambda I alpha I. And now it sort of makes sense to ask, suppose you knew that f was orthogonal to the all ones vector. How large can MF be in relation to the original f? So saying that f is orthogonal to the all ones vector is just saying that alpha 1 is equal to 0. So f is just something that involves v2 to vn. And we are asking how large can MF be in relation to f? Like what's the worst possible situation? Now, if you just stare at this above the norms that you have here, you notice that all the coordinates are going to get dampened down by the corresponding lambda I. So if you want to make sure that this MF is as large as possible, it makes sense to put all your mass on the largest possible lambda i's. Okay. So this is going to tell us that if you were to look at this definition, which is hopefully it's reminiscent of what we had seen earlier, which is look at all possible vectors f that are orthogonal to the constant vector and ask how much does m shrink that vector. It's easy to sort of check and basically convince yourself that basically the worst thing you can do is like take the vector whose take the eigenvector either v2 or the eigenvector vn. In some sense, basically the one closest to 1 or the one closest to -1. It could be the case that maybe lambda n is like somewhere here. Okay. And so another way of writing the spectral gap is to basically say that I would like to know. So, I mean, lambda 1 is anyway going to be sitting at 1. So there's no hope of that. But can I draw a smaller radius that somehow encloses all the other eigenvalues? The radius of that, that ball that you drew over the real line, that is a spectral gap. And this radius is going to be whatever the larger quantity, either where lambda 2 is sitting on this side or lambda n is sitting on this side. So those are the extreme points. So whichever is closer to the boundaries, I mean, that is going to that is going to basically tell what lambda of this is. And the spectral gap is basically the gap that you're guaranteed on either side. That is, you're guaranteed that there is no eigenvalue between 1 minus gamma and -1 plus gamma. Okay. That's the definition of what spectral gap, etc., mean for arbitrary undirected graphs. Okay, now that we have done all this, we are now in a position to actually prove the expander mixing lemma. But previously, we had stated the expander mixing lemma in the context of deregular graphs. But now we have set up the whole machinery where we are not dealing with deregular graphs, but arbitrary undirected graphs. So we'll have to make some minor modifications to the statement of the expander mixing lemma. Okay. So let's again go over this. M is a random walk matrix that corresponds to some undirected graph. And let's say gamma is the spectral gap that we are dealing with. And gamma is basically 1 minus lambda. Okay. Now suppose S and T are two vertices, two sets of vertices. And previously we were sort of saying that alpha was the fractional size of S and beta was the fractional size of T. However, if the graph is going to be possibly not regular, then maybe the fractional size is not the right measure to look at. So it turns out the right thing to actually look at is to ask the following, which is you pick a vertex according to the stationary distribution of this random walk matrix and ask what is the chance that that distribution, the vector that you drew, actually fell inside the set S. That is going to be the right notion of the volume of S in this context. And similarly, beta is going to be you pick a vector x according to the stationary distribution. What's the chance that it actually falls in T? All right. And now to look at this alpha beta now refers to the following. I'm going to pick x and y independently according to the stationary distribution and ask what is the chance that x is in S and y is in T. That's exactly alpha beta. The other side is now going to be I just pick an edge at random and ask what is the chance that the first endpoint happens to be in S and the second endpoint happens to be in T. So previously there was a 1 over capital ND in the denominator because we were dealing with D-regular graphs, but this is the more general notion that we could have. Okay, and the right hand side is again very similar. I mean, it's exactly the same error term as in the previous statement for D-regular graphs. All right. So the way we're going to prove it is it's sort of, I mean, like now hopefully things should be very clear as to what we need to do. If we look at this term, this is perfectly suited for using the bilinear form corresponding to the matrix N. And so we're going to just do the following. Just take the indicator vector of the set S and the indicator vector of the set T. And let's just focus on, I mean, I want to focus on the bilinear form corresponding to 1s and 1t. And as usual, we are going to try and decompose the vector into the component along the all ones direction and the component perpendicular to the all ones direction. Okay, and let's say that it is a times the all ones plus whatever is perpendicular in the, I mean, the 1s perp just refers to something that is orthogonal to the all ones. Okay. Of course, we don't know what what a is. This a is some whatever coefficient that you have, and we want to get a sense of what this a is. And it's actually easy to figure that out, which is thanks to the orthonormal basis and so on. If you care about the coefficient of the all ones vector, we just take an inner product with the all ones vector, and the orthogonal component just gets skipped. So the left-hand side's inner product with the all ones vector is basically going to be a times the inner product of 1 with itself plus 0. And it's easy to verify that the all ones vector has norm 1. So therefore, this is just going to be equal to a. Okay. But on the other hand, what is this quantity? Well, it's nothing but you are basically picking up a vertex x according to pi and asking what is the look at the expected value of the indicator variable that x is in S. And that's basically the same thing as the probability that x is in S when you draw x according to pi. And this is what we set as alpha. Okay. And in exactly the same way, the 1t vector is going to just be beta times the all ones vector plus something that is orthogonal. All right. And now is when this is the quantity we wanted to get a sense of. And the bilinear form is set up in such a way that this is exactly equal to the bilinear form of 1s and 1t. So that is, you look at the inner product of 1s with m times 1t, and that exactly captures the probability that if you pick an edge at random, that the first endpoint happens to be in S and the second endpoint happens to be in T. Okay. And we'll do the obvious thing of just decomposing 1s and 1t using the way we defined above. And now use the fact that m times the all ones vector is equal to the all ones vector. So m acts only on the orthogonal component in some sense. The parallel component stays the same. And now it's clear what to do. So this is an inner product of like two sums. So if we expand things out, we'll get 4 terms, and we'll just have to deal with those 4 terms. But it's easy to sort of see that, 2 of the terms are actually going to be 0, because this vector, whatever this vector is going to be orthogonal to the all ones vector. So therefore, the inner product of this with this is going to be 0. And similarly, the inner product of this with this is going to be 0. And if you just expand it out, what you end up getting is alpha beta times the inner product of 1 with itself plus the inner product of these orthogonal components. Okay. And so, and this we sort of already stated that the inner product of 1 with itself is actually equal to 1. And therefore, the left-hand side of the EML sort of naturally shows up here, which is that this is equal to this, which is the main term, plus a certain error term. So I'm just writing this as the left-hand side of the EML that we cared about is at most whatever is the inner product between these two orthogonal components. All right. So now, once again, I mean, like, since we have an inner product of 2 vectors, the most natural way to upper bound it is to use Cauchy-Schwarz. And this can be written as the norm of the first vector and the norm of the second vector. And now we can use expansion to pull out a factor of lambda and get rid of this m, because we know that the norm of m times 1t transpose is at most lambda times the norm of 1t transpose. That's by the definition of spectral expansion. Okay. So now sort of we know what we need to do. We know that the EML statement claims that it is lambda times something, whereas now we have it's lambda times something else. So naturally, we want to somehow show that this is square root of alpha into 1 minus alpha, and this is square root of beta into 1 minus beta. That's all that's left to do. Okay. And now why is that true? Well, let's again look at the decomposition that we had previously. And let's just look at the norm of either side. By Pythagoras theorem, the norm of 1s squared is going to be alpha squared plus norm of the 1 perp squared, because that's what I want to get a sense of here. Right? But what is the norm of 1s squared? That is nothing but the inner product of 1s with itself. And the inner product of 1s with itself is you draw x according to the stationary distribution, and you look at the indicator that x is in S times indicator that x is in S. And which is the same thing as saying you draw x according to the uniform distribution and look at the expected value that the indicator of x is in S. And that's just alpha, because this is the probability that when you draw x at random, you get an element of S. Okay, so that's alpha. So this immediately tells us that the norm of 1s perp squared is alpha minus alpha squared, which is alpha into 1 minus alpha. So plugging that in, that completes the proof of EML. All right. So hopefully today we now have a sense of how this slightly modified inner product is very useful when it comes to spectral expansion and dealing with these general, possibly irregular, undirected graphs. Most of the time we'll end up using it for directed graphs, but I think this generality is very useful to know. And in the next class, what we're going to basically be doing is we're going to get, now that we have the necessary language, we will start talking about how quickly do these random walks mix and get a sense of it, because that was a starting point of looking at spectral expanders in any way. And once we do this, we'll be able to analyze this rather like bizarre algorithm to check graph connectivity. Okay. So let's imagine that you have an undirected graph G and you're given 2 vertices S and T, and you want to check if S and T are connected or not. Now, the standard way to do this is to basically do a depth first search or a breadth first search or something. But notice that no matter whether you're doing a DFS or a BFS, your algorithm will start marking vertices to figure out which vertices you have visited or not visited. So in some sense, you need a lot of, you need to have space proportional to the number of vertices, because you might have to mark all of the vertices and so on. But on the other hand, the algorithm that is presented here is a really, really low space algorithm, in the sense that it's only going to remember one counter and a handful of vertices, like maybe 3 or 4 vertices. It's going to remember what S is, what T is, and maybe 2 other vertices. And the algorithm is a really, really like very simple to state algorithm, which is you start with the vertex S, and then you just keep going to a random neighbor, and you do that for about n to the 10 steps. So at every point, you're going to check, have I reached T? If I've reached T, well, I'm going to say, okay, I know that S and T are connected. But if I haven't reached T, I'm just going to pick a random neighbor of my current vertex and basically move there. And you just repeat it something like n to the 10 times. And if it so happens that you have not visited T until now, I want to somehow return. Okay. And we will show that this is actually an excellent randomized algorithm for graph connectivity. So with high probability, if it is the case that S and T were indeed connected, in n to the 10 steps, you will visit T with high probability. That's what we would like to argue. But at the moment, we are just slowly developing the language needed to make such claims, and then we'll put that to use once we start dealing with random walks in general and getting a sense of how quickly things works. Okay, and of course, this is a course on pseudorandomness. So after we do this a little later, what we will do is we'll de-randomize this algorithm. We will show that there is actually a low space algorithm, deterministic algorithm, to check whether 2 vertices in an undirected graph is connected or not in polynomial time and just logarithmic space. Okay, this is a beautiful theorem of Reingold. And that's going to be one of the results that we will see, I don't know, maybe 3 lectures from now or something. And this will require us to learn to build explicit expanders, which is something that we have not done so far. So far, we've only been discussing properties of these mysterious objects, but we will learn how to build these explicit expanders instead. So that's going to be the rough agenda for the next few lectures. And hopefully the next few lectures, I will record them without hiccups. Okay, that's it.